reckon I should turn that down.
So we ought to be live, everyone. That ought to be good. Though YouTube is having problems keeping up with us, but it tells me that we're all happening. So there are people there already. Some of the old favourites: Dora, Mute Donkey, Catnip, Jessica G, of course. Yes.
Nice to see them. But yeah, you're right. It's having a bit of trouble keeping up. So
can guys hear us?
Like I'm looking. Yeah.
Okay.
Oh, there we go. So you see how that took ages.
But good morning, Professor Phil.
Hey, good morning to you. How are you going?
I'm unused to being up at this hour. I'm going to openly admit. But
the older you get, the earlier you wake up.
Yes. Well, that just goes to show that there's a lot older I can get, which is a depressing concept. But all right. It's I'm hearing that your audio is a bit low, so I can try and fix that on my end with my dazzling technical competence.
Get it any closer?
Okay, so why don't I? No, I'm hoping that if I do this, keep on talking because you've got to.
Yeah. Okay. All right. No worries. Yeah.
I'm hoping that did something. Okay.
So, what was the clever thing that team did to so that YouTube could keep up with us?
Well, I think the thing was, I think YouTube has had some issues over the past little while. Last time Brainy Beaver tried to stream, it was a debacle all round, and
right.
And so I think YouTube has started having some serious problems with connectivity. But the the other thing is that team uses vMix, which is something like $1,200 of software for this purpose.
He must be. Oh, okay. Well, that's a very reasonably serious.
It is a reasonably serious commitment. He, if you've ever seen him do his recent performances in the super chats, he is a very committed individual, I have to say. I'm worried about his vocal cords in the longer term, and I live in fear of what will happen if he wants to join, because it will strain my technical competence to its sinews. But anyway,
it'll probably save the day. What are you talking about?
It almost certainly will. So today, the special topic that we chose last week was spacetime, and so just let's start by each of us introducing the concept to the audience, or our understanding of the concept. And so I'd be thrilled to hear. Okay. Is this something that you have to teach in the courses that?
Well, I think mostly by the time I get to students, they pretty much have covered that sort of stuff. So look, we do talk about it. We do go over it in some detail. I don't actually go through those 10 tensors as such. I think we're more focused on the practical aspects of general relativity, and but yeah, look, it depends on the course. But I have had the occasion to go through the entire thing, and it's quite a daunting thing. And being a mathematician is probably more like something up your alley
Right.
than mine.
Well, yeah.
So
I mean, my approach to it actually is just from the metric space option. So obviously we're introduced to who Minkowski is, and I think that sort of it's very easy from a mathematical perspective to ignore just how important Minkowski's contribution was, because he realized two things.
yeah,
One, that time was part of the position tensor, but he also introduced scaling of the time variable. Without that scaling by the speed of light, it's not clear that you can calculate meaningful distances in 4 dimensions, where time is one of the dimensions. And the other thing he did was introduce the change in sign, so that you could distinguish time. Time has time has that. Time has the opposite sense to the spatial coordinates. To take it back to its more basic fundamentals, space time. What Minkowski worked out was that while the passage of time and the distance between things was very dependent on an observer's position or velocity relative to another observer, there was an invariant. There was something that didn't change, and that was the length interval. And in mathematical notation, we call that ds squared, which is c squared dt squared plus dx minus dx squared minus dy squared minus z squared. And so it's the distance in time squared multiplied by the speed of light squared minus the spatial distance squared. And that is a constant element for all observers. And finding this thing
sums it up, basically.
And finding this thing that was the same for everybody is just allows us to start understanding the nature of reality, the paths that we are taking through this coordinate system. So that at least is how I come to terms with what's going on in it. And I'm interested in your response to that.
Well, look, I totally agree with you. I think from for the purposes of this exercise, we could bore them to death, the audience to death, by going through the mathematics. So what I'm proposing is to maybe throw around some ideas about trying to conceptualize space-time and what is it? What is space, for instance? What do we mean by that, and what do we mean by time? So I think we sort of briefly went over that last time, and so I mentioned that if you think about space as being some position, some place, so some place in 3-dimensional space. Okay, but as soon as you say that, some place in 3-dimensional, you automatically are now expecting that to be referenced. So you can't talk about a space at some place without referencing it to something else. You can't say I'm somewhere without saying where that is in reference to something else. All right, so space sort of doesn't really exist on its own either. And then when you then talking about your 3 positions, so X, Y, Z, you now have to somehow bring that to a single component. So say a single component of your grid. So the idea is about trying to understand how this three-dimensional position is a uniform distribution, if you like. Let's say it was a grid, and the grid situation is just really a means of
Yeah.
describing it. So if you describe some sort of uniformity about this three-dimensional space, and if you look at a Cartesian plane, you can sort of think about how that might be uniform.
Yep.
Okay, so that's our space. Now, time means whatever it happens to occupy anything in that space, or even if there's nothing in that space.
Yep.
Then time is still something that's moving in a single direction, and we can visualize time moving by just looking at entropy.
Yep, exactly.
Okay, so we've got a position and we've got something that's constantly moving, which then comes back to the idea that nothing doesn't move.
Yeah. Yes.
Okay. Movement is intrinsic to everything in the universe. Nothing doesn't move.
Yeah.
So now we have a position in time moving, and the time also is uniform. It's completely uniform in the same way that space was uniform. Now, accepting that both those things are uniform, you now introduce something else. So we're now introducing something with mass. So anything. It could be as small as a helium atom or a hydrogen atom, a single proton, or even a single electron. Introduce something with mass, and now all of a sudden the very fact that it now exists in this space and this time changes the space and time. Okay?
Yep.
So what we're saying is that this changes the space and time in such a way that as this object now continues to move through space and time, it creates this change that it's created moves with it.
Yep.
So Earth's gravitational field moves with the Earth going around the sun.
Yes, and
so that's kind of that's about as simple as I could conceptualize it. It is really, really difficult, as you know, to try and put to try and think of four dimensions. We're just not. Our brains aren't just.
Well, that's that is, and this is the genius, I think, of sort of the conceptualization is the realization that actually time and space aren't independent anymore. Once you've got mass, once you've got an observer, once you've got people looking at it, it's not just a three-dimensional problem anymore. It's a four-dimensional problem, and in the four dimensions aren't the perceived time between events in classical mechanics, the way, say, Newton or Galileo viewed the world, time progressed at the same rate everywhere, according to every observer.
Yeah.
That's a very difficult concept to give up on. It was Einstein who pointed out that actually you're not looking at an event that just happened. It happened a little while ago. And how long ago it appeared to happen to you is different from how long ago it appeared to happen to somebody else. And that insight, so the rate at which we're experiencing the universe, the time of events relative to one another, is different depending on where you are and how fast you're traveling. And but bringing it back to that line element, which you're right, the mathematics is pretty boring, but Minkowski identified this uniform constant that allows us to actually make sense of how time and space are related. And it's one of the things that I think is a bit when flat earthers, for instance, say, well, gravity is a magical force, to some extent, the bending of space-time by mass still isn't something that we understand fully. It still isn't something that we don't really know why it is that mass bends space-time in that way. We just know that it does.
Yeah, exactly. That is one of the fundamental questions still.
Yeah, and
so yes, we can go all the way back to that, and you're quite right, and say, well, okay, so why does? I think intuitively you'd expect it to.
Yeah.
Okay, because you have this quiet, uniform space and time and then now introduced something into it. So you'd expect it to change. Okay, you'd expect some sort of effect from that. But it still comes down to this why business. Why mass? Why not something without mass?
And it,
what is it about mass that causes this? To happen. So there's still a lot to be explained.
And there's this gets back to the quotes the flat earthers cherry pick about gravity isn't really a force. Which they're very fond. They're very fond of quoting Brian Cox when he says gravity isn't really a force. But when he says that he doesn't understand how a sentient human being can come to the conclusion that the Earth is flat, they conveniently ignore that and tell him that he's an idiot. But there's an argument to be made that what we see as the force of gravity is simply bodies flowing along the shortest path in space-time. That's.
Which again, you'd expect that to happen.
It's just a natural result of the curvature of space-time and the the fundamental laws of reality. So that doesn't mean that there isn't, from our 3D perspective, there isn't acceleration as a result, mutual acceleration induced between two bodies with mass. Once you step back into the three-dimensional framework, that's the best way to make sense of what we're observing. So it's a you can get really, really complicated, but essentially the purpose of science is to try and describe reality. It's to try and describe the universe and the events within it in the way, as we understand them and as we perceive them. And space-time represents a really key, I think, intellectual leap from classical science, from classical mechanics, classical science, up to somewhere where we can really understand the inherent energy inside an object with mass, or how the gravity at a more fundamental level, how light travels. There's so much understanding that we've been given, and we've been able to use spectacularly over the past 100 years as a result of our understanding of space-time.
Yeah, look, I think if we get back to helping our audience just understand a bit more about the space-time. And why things do accelerate. So that's the other big question, All right, then let's say we get our audience to accept that yes, the space-time, is or was this uniform arrangement that is now influenced by something with mass. Well, why do things that are close to this, or within the influence of this mass, why do they accelerate?
Yeah.
And of course they accelerate because they're forced to accelerate because they must now follow the contours of this new paradigm, this new existence. So they therefore forced to and energy is doomed to follow a straight line,
and that's its nature. It doesn't look straight to us, who are inside this space. but it is the path of minimum distance in the space. It's and so it's just the way that energy and matter flow, and that's a really great insight, I think. I'm going to step back a little bit and ask the audience if they are keeping up with us, because I think you're doing a really good job of being accessible, and I'm coming in and crapping all over it whenever I open my mouth at the moment.
I think you need to.
So how are we doing, guys? Is this okay? Is this is this at a level where you can grasp at least some of the concepts, or not? Because it's one of the things. Obviously, I just enjoy talking to Phil. So we can sit here having a good time, but obviously we're trying to do this so that we can give at least some deeper understanding of what's going on. Okay, so we're getting a
That's good. Good. The feedback's good. That's all right. Yeah. Look, okay. So the next thing is having described why it is that that things will accelerate. As they're forced to accelerate.
Yeah.
So what we can say about something in that's uniformly shaped. So like a sphere. So it's uniformly shaped now, influencing inside this space-time, so which we've now described. So it's because it's uniformly shaped inside this space-time, it creates a uniformly shaped distortion of the space-time. Yep. So this new distribution of the space and time, as it were, is uniformly distorted.
Yep.
So therefore, anything within its influence would also be uniformly moving. Yep. So therefore, we'd expect that two objects not affected by other forces would accelerate at exactly the same rate. They must accelerate at exactly the same rate. If they didn't, we can just throw this whole thing out.
Yeah, that's right. And I mean, I think this is stepping back to a more general scientific point. This is something that is poorly understood. If we could explain observed reality, all of the phenomena that we see, with a simpler model, with with something less complicated, we would, right? This is quite complicated, space time and tensors and the metric tensors and Einstein field equations, but we use them because they do a really good job of explaining everything that we see, and no other formulation that we've been able to come up with does as good a job. So we don't go around creating complicated intellectual concepts or formula or formulations for the hell of it. Or to torture students. If there were a simpler way of modeling the observed features of reality, you can bet your bottom dollar that we'd be using that and not this. But the fact is that reality is quite complicated. It exhibits some very non-intuitive behaviors, and we get and we have to resort to these more complicated mathematical concepts in order to understand what's going on. We just have to. It's not a choice. It's because this is the nature of reality.
Yeah, I think by the as we moved technology, towards things like orbital mechanics, to where we have things like satellites, GPS, and that, we are forced to take into account these other parameters. So previously, in Newton's world, you could deal with force and mass, velocity, acceleration, all these things as a group of entities that can work together, and they do. But then time is kind of separate. And even though in classical movement, of course, we do apply time, like ut plus half at squared, which describes parabolic motion, classic parabolic motion. So even though we need time in that essence, time still at the very core of this equation is still a different thing. Okay, so whereas we talk about distant and mass being somewhat related, we kind of throw time away. I'm pretty sure Newton understood that time was part of this, but just didn't know how to describe it.
I think you're right. So I am writing down questions that people have asked. We've had a couple of direct questions from the plot hole. I didn't write down the guy who had the question about escape velocity of black holes, but we will be getting to your questions. So do feel free to put them in the chat. And as I say, I'm writing them down as I see them. Rachie has a question that she just asked. What we're saying is there's basically almost like a warp field around masses. It's kind of one of the ways. It's a reasonable way to approach it. One of the way that there was a flat earther, I think, who I was seeing, and he was showing a picture of a heavy ball on an elastic sheet, right? And it depresses the sheet.
Yeah.
And then he came up and he pressed down on the elastic sheet away from the ball, depressed it so that it was lower than the ball, and the ball rolled towards his where he had pressed it. And he's gone, I didn't apply a force to the ball. Well, actually, yes, you did. You just actually demonstrated how gravitational attraction works. Because another mass distorts the gravitational field and makes the ball roll towards it, which is kind of a misleading analogy to some extent, because in that there's obviously a direction that's called down, and there's a force acting in that direction. And
I don't actually like that analogy.
It provides some degree of insight, but it is fundamentally misleading. But the key element that objects rest in a medium that is being bent is and it is that bending of the medium that results in these interactions. I think that is an important element to understand. But when you try and apply it more generally, as you say, it's not a valid comparison. I do want to address something, because Rachie and I had a bit of a blow up. Because Rachie's been around for 5 or 6 months as far it seemed I have to admit that I'm openly unhappy with sort of the lack of progress, because I kind of suspect that if because, for instance, just the geometry of the Earth, using the spherical distance formula, if you give me the latitude and longitude of any 2 points on that surface, I can calculate accurately the distance between them. That cannot work if the Earth is flat. It simply can't. It's impossible. Okay. I don't. Yeah.
Right, can I? Yeah. Let me just interrupt for a little bit. Okay. So no, I get where you're going with this, but may I offer a little bit of advice? Okay. So, and I found this from many decades of teaching. All right, and that is that you can't just assume that you can understand what's going on in another person's mind. So I have this philosophy, actually. If somebody doesn't actually understand what you mean, it's probably your fault.
That That could be true,
Okay.
it still frustrates me, and yeah.
Oh, there's absolutely no doubt
Yeah.
about that. The amount of times that I've been bogged down in trying to this is to students who are at the edge of graduating, where you're trying to this particular explanation didn't work. Try something else. Look at it from a different angle, and this is where the skill obviously comes in. You can't learn this stuff by watching YouTube videos, because there's no way known you'll be able to look at it from enough different angles to be able to explain it properly. And so when you're talking about somebody, like Rachie or some of the others, you've got you've had the privilege of having seen all of this all the way from the beginning. You've gone through A levels or VC or O levels, however you went through, or HSC, however you went through this pipeline, and having had the benefit of all the little bits that add up to what you know now. And what we're expecting them to do is to pick up from a long way in, and then we get frustrated because we don't have the time, or maybe even the inclination, to go all the way back and start all the way from the beginning, and say, well, this is how trigonometry works. See, let me explain to you the unit circle.
Yes.
Gosh, I can't explain to you the unit circle if you don't even know what an angle is, or a radian.
Yeah, it's...
How far back do I need to
go? That is the problem. I think that, sort of the... when you get to the point that... when you get to the point that trigonometry, the constancy of the relationships between the sides and angles of triangles... you're getting to the point. Well, it's not my job to teach you. It's not my job to actually teach you trigonometry. You should have learned that in school. My understanding is that everybody gets taught trigonometry in high school. It is not. It's not possible to get out of high school without having been exposed to trigonometry. And if you're
That's entirely true, Tony, but I can tell you this for a fact. It's badly taught.
Right. Well, that's a social issue, because I don't think we put anywhere near enough funding into having competent teachers in high schools.
I agree. That's entirely true. So what we're doing is we're getting teachers who barely know what it is themselves put into situations where year after year they explain the same things with the same errors that they always did have, and the same inconsistencies, and so the same limited understanding themselves go year after year after year doing this, and not doing any favors to the students. And it's just the lucky ones who get through this and then maybe end up having to use this later on, that suddenly figure it out and say, wow, that's what they meant. Why the hell didn't they tell me that when I was at school? Well, actually they tried, but they didn't understand it themselves. And I'll tell you, this leads to a very interesting study that I did with regards to mathematics education. So if you ask 10 people, just 10 ordinary people, and say, would you classify yourself as being good at mathematics? About 9 of those people would say no.
Yeah.
Now, that statistic actually is the same statistic in primary school. It's exactly the same one. So if you look at that and you can say, well, what are my chances of getting a teacher who knows mathematics? Enough mathematics to be able to explain it in different ways so that everybody can understand it, so that there isn't a factory way of explaining it, so that one size fits all. You've only got 1 in 10 chance of getting a teacher like that.
Yep.
And so if we look at that, then we say, all right, well, there isn't the same opportunities for everybody. Okay, so you've had an interest in the
Yep.
mathematics, so you've followed that, and for whatever reason, you just got the right teacher, so that the penny
Yep.
dropped. And once it did do that, then you could run with it yourself, and whatever you learnt was probably in spite of
You're
the
right.
teachers,
Well,
not because
well,
of the
yeah.
teachers.
I definitely had that experience towards the latter end of high school, but let me take this. Let me take this in a slightly different direction. So, if you're genuinely interested in science, if you're genuinely interested in understanding how the science works, then you need to equip yourselves with at least some of the mathematical tools necessary to understand that science. And trigonometry is
Absolutely.
one of the most fundamental ones.
Yes.
You need and rather than and there are certainly facilities out there by which you can teach yourself trigonometry, and it is somewhat frustrating to and furthermore, there are lots and lots and lots and lots and lots of people who understand basic trigonometry. I understand that there is a user called Basic Trigonometry in the chat right now, and it feels like I'm talking about him, but I'm not. But if you're rather than, for instance, requiring that I teach somebody basic trigonometry, perhaps people can find resources about basic trigonometry or find other people. It seems a little bit like you're using a dump truck to go to the store, right? It doesn't seem like an appropriate use of resources. And I'm not a high school teacher. I think I think I'm and I have a patience problem.
Yeah. Well, it doesn't matter what age, you need patience
Yeah,
anyway, for that. But I think just getting back to how we got
yeah,
onto this in the first place is that I think we need to cut some
okay.
slack and say, look, okay, I'm not going to be, I'm going to keep trying. So you wouldn't say to someone, like Rachie, look, I'm just going to give up on you because it doesn't seem like I'm ever going to get anywhere. I think the questions that she asks are appropriate,
I think
and they're appropriate to her. Put it that
Well,
way.
I think there needs to
Okay.
be a certain level of self awareness. One of the points to me was there's been a picture of the geoid that was put up recently,
Yeah.
one flat earther said, "Well, this is the shape you're claiming for the Earth." No, we're not claiming that's the shape for the Earth. We are claiming that that is a visual representation of the geoid, but it is vertically exaggerated. You don't understand that, and you're misusing it to claim that we're saying that the Earth is not spheroidal. It's some sort of bizarre potato shape, and
Yeah.
but let's look at the broader intellectual inference of this. Somebody with no understanding of geodesy is telling me, a geodesist, that their
Mm.
intuitive response to a picture is enough to disprove the spheroidal model of the Earth. No,
Yeah.
that's an unacceptable conclusion for you to reach. It's not the case that tens of thousands of postgraduate researchers around the world have seen this image and have failed to understand what it means. And I have to say it's more than slightly insulting that's the level of intellect. If you believe that that's my intellectual level, why are you even talking to me?
That's a very good point, and I think it does go both ways, as you say, because if they, I can understand them saying, well, look, I understand what you mean, but I don't accept it, right? But not that, say, look, you and accuse you of not understanding
Yeah,
your own model, or accusing you of not understanding. I agree that that's that's
Yeah,
not on.
it's and it's frustrating. Like it happened most egregiously with Mind of God or whatever. But let's address some of the questions. We got a couple of questions about this, and one of the interesting ones was from the plot hole. How does chaos theory and nonlinear response factor into this? And I think that's actually a really good one in terms of the structure of the solar system, right, or the organization of the solar system.
Yeah.
Do you want to address that, or?
Well, yeah. Look, I think. All right. So if we go right back to
Yeah,
entropy, and we talk about things moving from order to disorder. Okay, so let's say, for instance, you had a cylinder of jelly beans, and they're all layered in different in different colors. Let's say, okay. So you had thousands of jelly beans in a cylinder that you could see through, and they're all layered in different colors. And then all of a sudden, you just threw them out. They would not. Let's say you threw them up in the air and just let them fall themselves. They would naturally fall into into disorder. Actually, at the first time you did it, there would be some sort of distribution that you could predict. And then the more often you did that, the less and less you could predict for this. And eventually it would be total chaos. But actually, I don't actually think that you could apply that to the universe. I don't. I think it's not.
Well, I think that well, I would suggest that there is. So when because there's a thing called the three-body problem. All right, which is the gravitational attraction between the if you've got three bodies of a given mass, initial positions, and initial velocities, how does the system evolve? And this turns out to be extremely sensitive to the initial conditions, where the bodies are, how big, what their relative masses, and their relative velocities. And if you change those a little bit, you can get very different patterns, and that is a chaotic system, right? That's a system where a small change in the initial conditions leads to a big change in the configuration after some time. So actually, normally this is illustrated with three bodies of equal mass near one another, and you can see if you go to the Wikipedia page, it's a rather spectacular example of the shapes that end up being generated. And they go in all directions. And actually, Anthony Riley suggested that this was evidence that gravity doesn't work. Because according to him, obviously that isn't real. Well, yeah, it isn't meant to be real. It's a mathematical representation of what would happen if you had three bodies in an effectively isolated system. Can you prove that three bodies in an effectively isolated system wouldn't behave in that fashion? And he's just gone. It's not real. Anyway, that was when
I think that when you look back to the kind of mathematical work that was required, that Einstein required to put together the field equations, I'm not so sure, Tony. It's one of those things we might have to not so sure. Because I think there's a mathematical solution to what you talk to those states.
Absolutely, I think there is.
So if there's a mathematical solution to it, and we could predict it, then I don't know if we should call that chaos.
Okay.
I think,
yeah. So in a technical sense, a chaotic system is not one that is not unable to be modeled. It's one that where a very small change in the initial conditions will lead to a very large change. So that in a technical sense is what I mean when I mean a chaotic system.
And that's explained by general relativity, by the
Yeah,
way. So that's not a
yeah.
problem.
But the other element of this,
So Riley doesn't know what the hell he's talking about.
yeah, but the other thing is that we see this in sort of the gravitational perturbations. Earth's orbit is not stable, right? Earth's orbit varies slightly in ellipticity, in orientation. In
Yeah.
Earth's axial tilt varies, and its precession angle evolves over time as a result of gravitational perturbations due to Saturn and Jupiter. And these things seem very subtle, but they're actually important in driving the major cycles of the ice ages. Now, I am.
Are they predictable?
They are predictable, but they weren't initially predictable. And it turns out that actually the gravitational perturbations are only a small part of what's going on. It turns out that carbon dioxide and albedo feedbacks amplify this forcing in order to drive the glacial cycles. I just need to take a point aside because it seems like I really want the discussion in the chat to remain civil and for people to refrain from threats at all. And
sorry, I'm not reading the chat at all, so
that's
so
okay.
I don't know what's happening.
So I don't expect, I expect people to be grown-ups in the chat, and I don't expect grown-ups to necessarily get along. If you have a problem with somebody saying stuff about you, don't listen to them. Just ignore what they say, and we can all get on. I don't, I'm not going to sit here and tolerate threats of attack videos or that sort of thing. So if that's something that you're keen on, you are going to get. This is the only time I'm going to mention this. But if there are any future infractions along this line, the user involved will just be hidden. Okay, so let's. If you don't like somebody else in the chat, just don't listen to what they say, and let's all get back to learning. So
I just want to pick up where there's something I have to concede with regards to chaos.
Yeah.
I think you're right, actually. When I reflect on it, at the edges. So while I still think that mostly things happen, quite predictably in the universe, I think at the edges you're right, because small things can change. Let's say, for instance, the amount of gas that leaves the Earth. That if you like, that can change the system. So the Earth's gravitational field can change, all the time. And that tiny change can, as you said, can affect the perturbation of it, and all sorts of things at the very, very edges of it. So I agree with you in that sense. Yeah. So technically, you're right. Yeah.
It's I mean, we often think of chaotic things as just being extremely just utterly unpredictable. But there's
yes.
If it's in reality, it can be mathematically modeled, right? I mean, there's and if we knew the initial conditions exactly, if we had exact information on all of the initial conditions, we could model it quite well. Factard is apologising for the rock measuring thing. No, Factard, giving me a hard time is fine, and particularly calling me a geologist or a rock measurer it's profoundly insulting, but it's okay. I'll forgive you.
Yeah, I think you can live with that. It's okay. Yeah.
So I think we're both right. I think but what I found really interesting was that those tiny gravitational perturbations could be it can lead to quite dramatic effects. The glacial cycles are extremely large on the large effects on Earth's climate. And Earth's climate, it turns out, as you will understand, is very, very sensitive. It has positive feedback mechanisms that go both ways. That so it actually doesn't take much of a gravitational kick to do that. Hassan Halal,
which is the excuse, of course, that some of these anti-climate change deniers would use.
That's right. That'll be a topic for a later debate. But let's say I hate them with the white hot intensity of 1,000 suns. So Gently's channel asks if general relativity follows the inverse square law.
Oh well, it does. I mean, put it this way: there's something that if you accept that Newton's laws, weren't quite right, but they still work, and they still work with the inverse square law, so that obviously works.
That's right.
And in fact, it's written into the Einstein's field equation, so of course it does. So to answer his question, it most certainly does. In fact, the inverse square law is probably one of the most fundamental of all of the phenomena that we have. Light, electricity, you name it, applies.
Yeah, it's a. In that sense, yes, gravity obeys an inverse square law, and general relativity describes gravity. So, and it's built in there. It's a really, to my mind, I can't get over just how beautiful an intellectual construct space-time is, because people were trying to explain a whole bunch of stuff that didn't make sense, and just this ability to unify it. And we know that we need to understand it better. We know that there are things that we don't completely understand about this, but the fact that there is something that is unknown cannot be used as an argument to invalidate all of science. The fact that
which is what they tried to do.
What anti-science narratives are all based around. I am not. Just because Einstein came along and came up with a more complete description of gravity doesn't mean that Newton was at any point wrong, right? Doesn't mean that Newtonian gravity just gets thrown out the window as old, useless, and in no way applicable to real life. We don't bring out the Einstein field equations when we're trying to engineer a building or a vehicle or anything like that. We use the approximation of gravity that is most appropriate to the task at hand. For many engineering applications, it is quite sufficient to model gravity as a simple constant downward force of 9.81 meters per second.
Well,
for the vast majority.
I think what's misunderstood in this flat Earth community is this idea of precision.
Yep.
Okay, so in other words, I'll use just like they talk about 8 inches in a mile squared, which is parabolic motion.
Yep.
Right. So for any of you, if any flat earthers out there, if you've got one of your parameters is squared, then it's parabolic.
Yes, that's right.
If both of them are squared, it's circular.
That's right.
Okay, so get that into your heads. Now that is an approximation of the parabolic motion is approximation of this curvature, and it works to a certain degree. But But as soon as you move away from it, your parabola is moving, is widening and widening the further away that you go. It's only where you're really close to the apex of it where the approximation actually works.
And it only works over a very short length scale. You can't extend it indefinitely, and it's the further you go, the worse it gets. And
but if you're not interested in the precision, then it does work. If all you want is a few miles, yes, it does work. It does work because that's all the precision you want. But if you actually wanted to get even further precision, like say to the millimeter or something like that, it definitely wouldn't work. Now, if you're just talking about something plus or minus a mile, sure, or a kilometer, sure, okay, that works within that sort of precision. But as soon as you talk about something that needs more precision than that, it becomes plainly obvious that this is a parabola, and that would never work under those conditions, under that sort of precision. So therefore, now you have to use a circular function. And as soon as you start using the circular function, you realize that, hang on a second, the Earth is actually spherical. And one simple test that almost anybody can do, and certainly those people who have a field of wind turbines near them, just look across at the wind turbines and see if you can measure the angular height of each one, and then plot that against the distance between each one. And I guarantee it, you will find that y squared equals to r squared minus x squared. That is a circular function. This could not happen if it was flat. It would be a linear function. Y is mx plus b.
It's a remarkable. It is again. It gets back to the sort of frustrating element that there are so many ways that they could discuss this. That we know that stuff works. Like and again, all you need to do, all you need to do if you're a flat earther is show me 2 points on Earth's surface where the spherical distance function doesn't work. Just find 2. They could be wind turbines, they could be something else, but just find me 2 where it doesn't work, and I'll start taking a claim seriously. Team Skeptic points out that Newton understood that he didn't understand where the force was coming from, and it's that sort of understanding that sort of makes him even more of a genius. He was pretty genius all around. Not necessarily the nicest individual in the world, but he certainly was a genius.
Newton's actually my hero.
Oh, really? Okay.
Yeah, and because the not just because of what he did for universal gravitation, but also because of the mathematics. Because Newton put together the concept of calculus. Now, we both know how difficult that is.
Yeah.
We both understand what it takes to actually do that.
Yeah,
Imagine if you and I didn't have calculus. Now, if we didn't have calculus, we now have to think about how could we put that together. So how do we make these thin slices, for instance, a continuum, working out the area under a graph, for instance, a curve, How the hell would you do that, more and more accurately? And then Newton comes across with this. We're talking about somebody who's in his 20s.
Yeah, that's right.
Who came up with this? I guess if there's anything that annoys me more, and that is some flat earther who's left school at 15, who says Newton's an idiot.
Oh, yeah, that's right.
When someone says something like that, I've got to give up on them, I'm afraid.
So, yes, Rachie said she Googled the distance between Russia and USA and got 3 miles and 5,000 something miles. Yes, Russia and the United States are not actually points. They are large areas, and how you calculate the distance between large areas, do you calculate the minimum distance between 2 points within each area, in which case it would be 3 miles, or do you calculate the distance between their capital cities, or do you calculate the distance between their centroids? It had...
Or the Bering Strait.
That's right. The Bering Strait between Alaska and Russia is actually quite narrow, and there are American islands that stretch out into it and Russian islands that stretch out into it. It's not actually a good idea. Try picking 2 cities and looking at the distance there. But if I've got two books, should I be measuring from the center of this book to the center of this book, or from the nearest corner of each book? It's you need to be, when you're looking at distances are best defined between 2 points, not between 2 areas.
Again, it's precision. How much?
It's how much precision do you want? The spheroidal approximation is not actually perfect because the Earth isn't actually a spheroid, but it is very, very accurate, and accurate enough for most of the applications where we're going to, we have to deal with. There wasn't.
It's certainly accurate enough for orbital mechanics.
That's
or something
right.
Like that.
So I don't. There is another question, which is more about black holes. Do you want to?
Okay, you can go with that.
So the question was: is a black hole defined by having an escape velocity higher than the speed of light, or just slowing down the speed of light? That's a...
Well, it's the one thing that consumes photons.
Yes, that's right. So I think it's the former. I'm not sure that I'm not sure that the speed of light is being reduced because that's medium dependent. It's more that you've got such a steep gradient that the light doesn't have enough to get out and over the light doesn't have enough energy to get out and over get out of the well, essentially.
I think that's probably
so. That's certainly how I would describe it. That being said, I'm not an astrophysicist, and we're getting into areas where I need to think carefully before committing to an answer. So.
You got to be very careful. Unfortunately, you can sit there and discuss things quite openly in a lecture hall or in a tutorial, and nobody's going to make a clip of it and say, "I'm going to hold this against you."
And
they will.
And that's fine. And that would be an issue if I gave a rat's ass about what flat earthers think or say.
That's true.
They seem convinced that they are relevant and important somehow. I've had attack videos made about me by Quantum Eraser and Nathan Oakley and Anthony Riley and Bev course. And all sorts of stuff. I've never watched any of them. I just know that they exist because I couldn't care less.
You haven't matured if you haven't been attacked by one of them.
Now we're coming up on an hour. Now, do you you mentioned that you had some stuff that you wanted to talk about from our friends across the intellectual chasm.
So what I thought about was if we set aside, so just to plan this and see what the the peanuts out there think. If we sort of talk about science, a particular topic in the first hour or so, and then we can cover some of the silliness after that. Now, for instance, I and this segue into your video on the atmosphere. I think one of the things we should try and nail are the key things that the flat Earth people rely on, and one of these, for instance, they need to disprove gravity. So they say, well, gravity doesn't exist. Well, and then they fall off a cliff, and you think, well, there's gravity for you. Oop, there go gravity.
Yep.
As the song goes. So we need to cover these key things, and I thought it would be timely because of your video recently. Was this idea of you can't have gas pressure next to vacuum? That thing, but more importantly, the complete misuse of the second law of thermodynamics, which is what you covered, and striking in that is that the second law of thermodynamics refers to an isolated system.
Yeah. Well, it's. I think it's more than. Yes, thermodynamics describes the universe as a whole. Entropy inside the universe as a whole is increasing.
Yeah.
And there are systems that are effectively isolated, but Earth isn't one of them, because Earth is receiving a lot of energy from the sun.
Yes,
so.
Of course.
And radiating it out. So there is energy flow through the Earth system, to Earth's surface, re-radiated as infrared up into the atmosphere, and then radiated to space from there. So Earth is not actually a closed system. Earth is inside a closed system in the sense that, inside an isolated system in the sense that it's inside the universe, but it's also inside an effectively isolated system in that the solar system as a larger entity, wherever you want to define it, let's say twice the radius to the Oort cloud, the solar system is, under current circumstances, effectively isolated. The rate of energy flow into and out of the solar system is not that large.
No, it wouldn't be, because there's sufficient gravity in there to keep everything together, as it were. So yes, so quite right. Yeah.
It's it's a weird argument to bring up, but entropy, the fundamental thing that keeps the atmosphere close to Earth is that an individual gas particle can only go a certain distance straight upwards against a downward force.
Correct. Exactly. So eventually it's going to lose that energy.
It's going to lose that energy. The conservation of energy demands it, right? As it goes up, it's acquiring potential energy. And so it loses kinetic energy, and eventually it's going to it'll lose enough kinetic energy that it can't get any higher. That's all that's happening. And entropy is not going to give the gas particle more energy. It's not applying a force to the gas molecule. It's irrelevant to it's irrelevant to how high the gas molecule can go.
So that's extremely well said, and let me have a go at it slightly differently, okay? Which is pretty much saying the same thing. So if you are a flat earther up in the chat there, or lurking, and this is actually how it goes, right? So closer to the Earth, closer to the ground, there is a lot more energy, because the Earth is heating is warm compared to what's around it, and so there's a fair bit of energy around the Earth. and gas particles will move in all directions as you'd expect it to. And some of those directions will be down. And when we talk about pressure, for instance, we're talking about, and you've got an instrument, how much of the gas molecules is hitting up against that instrument?
Yeah, that's right.
Okay, that's what's being measured. Okay, so now as you get higher and higher up, the gas molecules are only going to get so far because they've got this thing called gravity working against them, working against the energy. So eventually they're going to stop getting up. But right up there around 100 kilometers or thereabouts, there's still gas molecules with sufficient energy to be able to escape. In other words, to be able to overcome gravity at that height. And these molecules do escape.
Yeah.
We're losing about 90 tons or thereabouts of gas molecules per day. I think it is. I stand corrected if that amount's wrong. But we're losing gas molecules all the time. These are the ones that do have enough energy to overcome the amount of gravity. But mostly they don't. Thankfully for us.
I mean, to some extent, there's an anthropomorphic argument, right? If things weren't suitable for humans to exist, then we wouldn't have to.
We wouldn't
yes, that's right. So there have been a couple of, in this argument, there have been a couple of questions about what constitutes a vacuum and whether or not it's true that vacuums have absolutely nothing in them, and sort of. In the general sense of gas pressure, you actually don't ever get to a point of having zero pressure. There'll always be, a faint amount. I think in interplanetary space, it's like one hydrogen atom every 2 cubic meters or something like that. So you are going to get some impacts of hydrogen atoms against any surface. That is going to create a force. You divide by area, you get pressure. It's just that it's so tiny. It is really difficult to measure. The impact of an individual hydrogen atom against a meter squared. Not exactly a big amount. And so the.
No, you'd be waiting with your instrument a little while before you got one.
And then, but the other thing is, if we took the air around us, and we put all of the molecules, we took all of the gas molecules and we compacted them into a tiny bit, it would make up less than 0.1%. Of the volume. The gas molecules in the air at sea level constitute less than 0.1% of the volume. So there is empty space around them. But that empty space is not necessarily, even if it's in interplanetary space or if it's in between the gas molecules on Earth, it isn't necessarily always empty. Because there are spontaneous creations of particles and antiparticles that sort of pop into existence and then annihilate one another for no net change. And this is called quantum foam, I think. And so the concept of a place where there's actually nothing. Is not necessarily well defined.
That would be a low.
Yeah, that's a very low probability. So there's generally stuff in energy and matter, and so vacuum is one of those terms that gets used by scientists. We created a vacuum and we dropped the bowling ball and the feather, and they fell at the same rate. They didn't create a total vacuum. They created pretty close, as
Enough.
close
Okay.
enough
Okay.
that they
Yeah.
could get accurate results from that. But it wasn't a complete vacuum, and it's one of the things that
Yeah.
it's one of those words that scientists throw around. But when scientists use it, they understand. Well, it isn't a perfect vacuum. It's still got stuff in it, but
Yeah.
just not much stuff, and enough that we can kind of ignore air resistance or that sort of thing.
F- flat earthers think about vacuum cleaners when you talk about vacuum. That's it. They don't have this idea that on one there must be energy on the other side in order for this vacuum to
Yeah.
happen. Okay, so I think they completely miss this concept about vacuum. So they talk about they think, well, why isn't everything getting
Yeah,
sucked away?
and it's a
As if the vacuum out there has got some sort of energy that's sucking
yeah.
energy that's with it.
Okay, and I wanna give a shout out to Team Skeptic who has been in the chat. We are
Yeah.
because not only immense gratitude for helping out last week, but we are keen to have you on as a sort of a regular conversation
Yes,
partner.
please.
But at the moment, one guest is straining my technical competence. So next week, I will have improved my technical competence enough to have you on.
We could just use his confidence.
We could, but he has other obligations. I'm trying to. I'm trying
Yeah.
to. You know.
Listen, I wanted to throw something
Yep.
by you, and this. Think about this. Imagine that we've worked out that the gas molecules don't have enough energy to escape, and so we end up with an atmosphere. Let's say we were hit by a massive asteroid, right? That would create a lot
Yeah.
of energy. Technically speaking, we could lose the
Yeah.
atmosphere.
Yep. Absolutely.
So that would be something worth thinking about. That's how, well, maybe not worth thinking about, but but that would be something. That would be something catastrophic from Earth. So not only would you'd have you could probably have dust take the place of the atmosphere.
Yeah. I mean, and that's the thing. If you change the system, you introduce more energy into the system to blow off the atmosphere. Yeah, the system is going to respond, but it's going to respond as it is forced. And we only need to we understand that eventuality well enough to understand that we really don't want it to happen, and we should take steps to avoid it.
Well, apparently we came within, I think, 4 million miles
Yep.
of that happening,
Exactly.
which is
It
pretty
is pretty
close.
close. I mean, in terms of interplanetary space, and we've actually been quite fortunate so far to avoid them up to the point where it becomes an option for us to start intervening in the orbits of asteroids and asteroids and near Earth objects. We've got the ability now to detect them and intervene in their change their paths. It's not easy, however, and when people talk about reduction of funding for these events, it's quite difficult to just emphasize. Well, actually, these things are hard to see. It takes a lot of effort to, and we need to see them early if we're going to want to do anything about them.
And you don't need something very big to be catastrophic.
Yep.
Now, so one of the things, again, as you said, it's not luck because we're here because these things are in place.
Yep.
But it's all of these things in the solar system, if you like, that are mopping up these things that are dangerous to us.
Yeah.
Which is a great thing, that all of this works. And of course, if you look back, we wouldn't exist but for the fact that all of this does work.
Yeah. It is amazing because the system could be prone to multiple perturbations, like multiple we talk about chaos. We talk about how sensitive things are, and particularly when you're talking about spinning vortices of protostellar dust. Where the planets form, the density anomalies that ultimately lead to planets, the clearing out their orbital paths, all of that sort of stuff. It's an extremely intricate mechanism, but it seems to be very, very reliable. Where we not too long ago, I think when I was an undergraduate, the possibility existed that actually planets were extremely rare objects. We didn't know, but now we see that they're everywhere, and so this large-scale imposition of structure and order into generating gravitationally stable bodies that clear out their own paths. This seems to be a fairly reliable thing, which is remarkable. It's just remarkable that the laws of physics work out that way.
Yeah, and I think that's a good segue because to this, and can I suggest that next week we have a look at light? I think that'll probably take about 3 sessions to look at light properly.
Yep.
But why don't we have a look at what light is? For the people might be. We talk about light a lot and electromagnetic radiation.
Yeah.
So I reckon that's something worth looking at maybe for the next time. What do you think?
I think that's a great idea. I think it's also a good stepping stone because a lot of what we know about the shape of space-time comes from observing how light moves, how light behaves.
Yeah, exactly.
And so it's the characteristics that light exhibits that actually led us on this entire journey that ended up with relativity, and indeed quantum mechanics. Sort of coming into the 19th century, nobody had any inkling that we would end up needing either quantum mechanics or relativity, but gradually the observations accumulated to suggest that things aren't as simple as we had assumed they were.
Yeah, so I would talk about light, and one of the things about light is, as you rightly point out, we wouldn't be interested in stars except that we can see them.
Yeah. That's right.
But then there's this concept of they're so far away. How come the photon doesn't stop? And why is it that we can't? This idea that if you can see it, the photons are hitting your retina.
Yes, that's right. That used to drive me.
You can see it. So I reckon dealing with having a look at light and how it might travel, and also maybe discussing how the sun produces photons might be a good.
That's a good idea. Because of course the light that we see coming from the sun is actually thousands. Most of it is, the vast majority of it is about 10,000 years old.
Yes.
We think of the sun as only 8 light minutes away, but those photons were actually created about 10,000 years ago. Before they get to us, and it's quite eye-opening when you start sort of thinking about that.
Which makes you think. Which makes you wonder. There's a whole bunch of questions about that because it makes you wonder how the hell would aliens get here if in order for them to travel that distance that they would need to, they'd need to be the size of light, and then it would take them 10,000 years.
Yeah. That's right. There are people who are, sort of trying to come up with ways of traveling faster than the speed of light, but I kind of think of it as a cosmic speed limit, and I'm pretty skeptical that we'll ever manage to get there. But and part of the reason is that's part of the reason why I don't think we're ever going to encounter aliens.
Actually, we should clarify this. There's no reason to suggest that there might not be some microbial aliens.
Yeah, that's true too. Yeah.
Because I mean, we do. There are comets
Yes.
that come from a long, long way away,
Yep.
and there's no reason for them not to have some
So
sort of microbes on them.
I'm not sure if you know Dial Wickramasinghe.
No.
He was an astrophysicist at ANU. He taught me astrophysics, but he was
Oh yes, I know who you're talking about. Yep.
he was one of the three brothers. They all ended
Yep,
up
yep.
being astrophysicists, and
That's
he
right.
did
Yeah.
some research on IR absorption by comets, and he was fairly convinced that at least some of them have microbes on them.
Yeah, oh, yeah. I would just looking at the probability of it not having microbes would be pretty small. So I would say they would have to, and it probably explains it probably explains life on Earth after Earth formed. Then if not all of it, but at least some of it, it could explain that life on
It could
Earth.
explain life on Earth, but it's hard. But it just sort of that just extends the question to some extent. I can more easily understand the generation of abiogenesis.
Yeah, I agree with
Yeah.
that, and it's one of my pet things. I've actually got about two or three videos on abiogenesis and how that would work. Is that fundamentally my degree is chemistry.
Oh, really?
So yeah, so I started as a chemist. Yeah, so I actually my initial work was in explosives. So I started. Yeah. So anyway, and looking back at those so we've got hydrogen and nitrogen, which are naturally going to go together. And at that time, a complete lack of oxygen, which of course you don't need when you've got for some organisms don't need any oxygen at all.
Yeah.
So hydrogen and nitrogen getting together, we're looking at creating amino acids.
Yeah.
And then from there building up long chains and long chain peptides, and then peptides creating proteins. These are all easily understood.
Yeah.
The thing about it is, though, is that exclusive, though? Would you say that this was the exclusive way that life formed, or could some of it be? Because essentially, why wouldn't life also have formed on the comets like that?
Well, what I think would be necessary would be a reasonably high energy flux in order to sort of move through the various combinatorics that are necessary. And so for a comet in sort of deep, a comet somewhat removed, that energy flux is going to be lower. It's not impossible by any means, but I think, sort of, it strikes me as and this is the thing, we're talking about probabilities here. It's not impossible that you're right, and that it was deposited here as a result of cometary impact. I will, however, say that it seems unlikely. What does seem very unlikely is that you could biogenetically generate two life forms that have compatible protein structures. So the general consistency of protein structures on Earth would tend to suggest that you need to have a single source, whatever that might be.
We need to go and find one of those microbes.
Yeah, that's what we need to do.
Yeah. So Tony, I'll just interrupt. I've got a question for Rachie. Now that we're on the topic of comets.
Yep.
Where do these comets hide under the dome? And how come we can predict when they're going to be there, when they're going to come out? So the flat earthers believe that there's a dome over a
Yep.
flat Earth. I'd like to know where the comets are hiding.
So it's yeah, it's a good question. And particularly the predictability of it. Like, we can predict
Yeah,
two within a minute, sunrise and sunset on
yeah,
Earth. We can predict two within the second. Eclipses and eclipse trajectories. And in fact, our understanding of eclipses, I keep on bringing this paper up, but there was a guy from
yeah.
Harvard University, not in a duck suit, who did a paper showing that recent sea level change is actually fairly recent. And the way he did this was by saying, let's assume that it's been happening all the time over the past 4,000 years. Then
Yeah,
that's going to change Earth's rotational moment of inertia. And
yeah,
that's going to change where the eclipses occur. And so he did a comparison of eclipse locations and times against historical records, and he showed that where they did occur was absolutely inconsistent with the concept of sea level being constant throughout that. So it's just our understanding is so detailed that we can actually use these systems to answer other scientific questions. We can analyze, we can identify changes in the length of day on Earth in response
yeah,
to earthquakes, right?
yeah. That's right. Yeah,
It just we are making these and we can understand the physical principle. Earthquakes, sort of, in a lot of earthquakes involve sort of upward vertical displacement as two systems stress one another, and then there's a relaxation and a collapse. Mass moves closer to Earth's center of mass, so the Earth speeds up. And
yeah,
it all fits perfectly well. None of it fits if the Earth doesn't spin, if there's no center of mass, if it's just a disk. We can make, we've got incredibly detailed understanding and numerical validation, observational validation of what's going on. And it just, to suggest that it doesn't, make sense, it's a dispiriting option. Anyway.
yeah. All right. Well, I need to move on. So
Okay.
I think maybe if we go for an hour and a half,
Okay.
do you think that's a sort of a reasonable
I
time?
think that is a reasonable time. An hour and a half is good.
Yeah,
Let's
yeah,
let's everybody get to work by 9 o'clock in the morning. I'm sure
yeah, yeah,
there
yeah.
are
Okay. So yeah, no, that's good. So it's been great. So let's do this again.
yep.
And next time, and next time we'll have a look at light,
Mm-hmm.
and we won't be able. I'm pretty sure we won't be able to do light any kind of justice
No, not
in
at
that
all.
small amount of time. But at least let's look at the beginning
Yep.
of it
And
and give some people an inkling of what it is.
yep. Well, I hope everybody enjoyed today. If there's any feedback on how we could improve it or how we could do a better,
Put it in the comments.
yes, leave it in the comments, and we will get back to it, and we will take it on board. We're trying to, obviously we're still learning our way through this, so the suggestion, we're not instantly perfect.
Yeah,
As great a triumph as the last stream was, we do understand that there may be some small imperfections that the more experienced YouTubers might have noticed. So we're
we do have an expert. All he has to do is come on.
well,
This-
we will definitely make sure to have Team on next time round.
yeah,
We choose to go about it. I want to give a special shout out to Crafty Keeler. Always wonderful to see her
yeah.
in the chat.
Always good. Yeah.
And Pixel Domination wants us to bring pictures. You're scaring me now. It was hard enough getting me in, but I'll try.
Yeah. I reckon. I think we will need Tim for that.
Yes, we will need Tim. But I'll, yeah, so next week, Light, episode 1.
Yes.
Yeah, thank you all so much for coming and for coming along and watching. We really do appreciate it.
Yep.
We're hoping this is helpful to you. Any
Okay,
last
so
words
I'll
from
let
you?
you end it all.
Okay. All right. Well.
Okay. See you later, Tony.
See you
Good
later.
talking to
See you later, Phil. See you later, stream.
Okay.
Talk to you and on.
Okay. All right. Cheers.
Yeah. And we're out. Yep.